Hey guys, this is Mr. Wang. So I'll be your physics teacher for this year. And sorry that I can't be with you guys at the moment because I just came back from China and where there's a big outbreak of coronavirus and it has been quite bad. But my city haven't been hit yet. So, but as a precaution, that I was required to stay at home for 2 weeks and before I can return to school. So that's why I'm taking this video so that you guys don't fall behind. So year 13, as you know, is a bit of a step up from year 12, and you've already seen the step up and experienced it from year 11 to year 12. So you know that it does require quite a bit of work. So if you've got a merit and above, congratulations. So you've done quite well. That shows that you have a good understanding of level 2 physics. So if you got achieved or some parts you might not even got not achieved, so that means the understanding was a bit lacking. So that means this year you have to work a bit harder than last year. And so as you go, then you will see how every day I'm going to be teaching something new and the concepts can be quite difficult. And sometimes the concepts is not difficult, but the question could be difficult as well. So it's very important for you guys to do homework every day and just make sure that whatever I give you and you understand it, and also give me feedback and let me know that okay, so I'm struggling and I need some help, or like I'm be running a physics tutorial this year as well, so which is on a Friday. It was last period last week, but so it's gonna rotate every week. So come to that as well. So I'll be able to give you guys some help. So anyway, just anything like send me an email at v1. So it's WANG VWANG at apps.school or .x.school.nz. Yeah, so then I can answer your question. So for today, so we're going to be starting with mechanics. So I want to talk about conservation of momentum. So conservation of momentum, you guys have already learned it last year. So basically, what is momentum? Momentum does not exist. It's just something like we invented, right? So this is what science is. Science is we're inventing things, and we look at the natural world that exists around us and we try to interpret and find some rules behind it, so then we can understand how it works and eventually we can use it for our benefit. I think they take this coronavirus as an example. Well, 500 years ago, if the disease exists, like nobody knows about it and they don't know how it spread, and like this, and half of the European population is gone because we don't know about it. But nowadays we know about it, and even though we can't cure it yet, at least we know and what it is and how it can spread. So then we try to contain it in a certain area that it does not spread to other areas. So, and as you can see, science has been really helping us, not just simply, oh yeah, I got to use my phone and now I can, take a TikTok video or whatever, all these new things that comes out every year, but also that in a big way, it saves our lives, right? So I was reading a book last year. It was talking about how the human have historically, like human have like three biggest enemies, and these three things, if they happen and it kills a ton of people, and then there's just nothing that you can do about it. So one is if there's a war. So if there's a war and then all of a sudden lots of people die, and then the second one is a famine. So if the famine happens and then you don't have food, say the weather was not good for a whole year, or there were a lot of wild bugs coming over and eat all the crops, so then lots of people die out of that. And then the third one is epidemic, so which is like a virus, a disease that gets spread out. So I think through technology, we've actually basically solved all these problems. I mean, for example, like food, famine, like nowadays, like with biology, and we crossbreed these plants, and we make sure like the plants we get grow like really big fruits. For example, kiwi fruit, right? Kiwi fruit is a typical example. It was a very small fruit called a Chinese gooseberry, but we have breed it and we want it to be bigger, more juicier, and we want it to be more sweet and or a little bit sour. And so now we got this like great brand of kiwi fruit, and that is owned by this company called Zespri. And Zespri actually owns this breed of kiwi fruit, and nobody else are allowed to use it because they've created it, they've breeded it, and then and then they got the right to export it. So that's why all the kiwi fruit exported in New Zealand under this breed brand because that's their breed. So how did I know that? I actually used to work for this breed. I was packing kiwi fruits in some kiwi fruit pack house in in Bay of Plenty, yeah, when I first came to New Zealand, and I was surprised because I was in 3 different factories owned by 3 different companies, but they were all exported as Lesbury. So I was like, oh, why is that? So then I find out, okay, it's actually they're actually breeded. And same with banana. Banana used to be very small, right? And then now we got it much bigger and more fruitful and more resistant to disease, and so yeah, and with war, I mean, nowadays we travel so much, so people got a much better understanding of each other. And I think the main thing about war, one is for people to get resource. So, and then the second one is to get is a misunderstanding people that have. And nowadays, so many people travel and around the world, and they just got to mix together, and then now people know each other better. So I think that is slowly being solved. Except some parts of the world, like it's still quite a bit of that happening as well. So anyway, that has gone on a bit of a tangent. So yeah. Anyway, regarding to year 13 of physics, so this year you already know that you're doing 3 externals and 2 internals. So we're starting with this external. Okay. All right. So coming back to this conservation momentum. So momentum, yeah. So we designed momentum. We call it, okay, if we times the mass by a velocity of an object, then we call this quantity momentum. So why do we call this momentum? That's because when we were analyzing situations with collision or explosion, and then we find out, wow, these 2 qualities, if we time them together, and there's a rule behind it. So people have done thousands, if not, tens of thousands of experiments in how to ball bouncing into each other. And at the end, they find out, like, wow, if we times the mass and the velocity together, actually this product, which we call the momentum, will stay the same. And then let's call it the law of conservation of momentum. Okay, so what is the law of conservation of momentum? You've learned it last year. Is the momentum of a system will stay the same unless there's an external force acting on the system. So if there's external force acting on the system, then there is an impulse. And you've learned last year, impulse is a change of momentum. So it's a product of force and time. Force times time, if a force acting on an object for a certain period of time, that will change the momentum, okay? So here, this year, one key thing we need to know is we're talking about system here. So what is a system? A system is not just one object, rather it's multiple objects together. So at least 2, normally we can call it a system. Otherwise it's just an isolated object. We wouldn't call it a system. So yeah, so how do you know, like say at the end of the year, you got to get a big paper. One of the most challenging thing for you guys to do is like, okay, so I've understand all these concepts and I've done really well during the year, but this particular question, like what is the concept that I need to use to solve this problem? So that's when you would need to practice a lot of papers and get used to it. But I'll tell you one trick over here is if you see the situation is a collision or explosion situation, then you know that it is very, very highly likely. I wouldn't say 100%, but I would say 99.999% you're going to be using conservation of momentum. Okay, all right. So say one year it was this. It was in a circus. A person was in a swing. So the swing, and then it come down and grab the other person, and then the 2 of them started swinging together. So yeah, so that is actually using conservation momentum. That is actually a collision situation, and then they started going together. So when you analyze when they are hitting each other, so that's when you're using conservation momentum. The momentum of this one is going to be transferred to become the momentum of these 2 together afterwards, okay? All right, so the key to solve all questions is whatever question you have, bang, you put it down. Momentum before equals to momentum after, okay? So if you write it down, sometimes you get achieved already just by saying that, putting that down, okay? All right, as you can see in the notes that I have this arrow on top of P before and P after. So you know that momentum is actually a vector. Why is that? That's because P equal mv, because if velocity has a direction, and then the momentum will have a direction. So that is why P equals mv, momentum have a direction. It's a vector. Okay, so if it's a vector, then we know 1 plus 1 does not equal to 2. It could equal to 2 if the 2 of them are in the same direction. So say force pulling this way, 10 Newton pulling, and the other one is pulling 10 Newton this way as well. So 2 pulling, so that will be 20 Newton, right? But if you have a situation where the 2 of them are pulling opposite direction, so this one is 10 Newton, this one is 10 Newton, actually together they will become 0. Okay, or if you go sideways, so if one is pulling that way, so one is pulling that way, and then you will start to go into the middle, right? So it could be 1 plus 1 could equal to a value that's anywhere from 0 to 2. Okay, so that is 2. Say this is 1, this is 1, that is 2, and 1.9, 1.8, 1.7, 1.5, 1.6, or whatever, you use your Pythagoras to figure it out, and then bam, when they're going this way, and 1 plus 1 equal to 0. They cancel out each other. Okay. All right. So now 2 types of questions. One is a simple one. You guys have been practicing last year, the one-dimensional questions. As you can see, it's still a little bit tricky. So, but what is one-dimensional? Like this is one-dimensional. If it's going to the left, it's either left or the right, and that's one-dimensional. Okay. If you're adding, say, north, south, west, east, so now you have 2-dimensional. You have your x and you have your y. That's 2-dimensional, right? Okay, so what is 3-dimensional? 3-dimensional is x, y, z. So you have another one going upwards. So then that is 3-dimension. So the space that we live in is 3-dimensional. So we can go forward, backward, left, right, or up and down. So our book you've experienced last year, you can go up, down, left, right, out of the page, and into the page. Okay, so that's why you got 3-dimensional, but we don't deal with 3-dimensional at level 3, so that's something you have to learn at university. So at the moment we're only dealing with 2-dimensional, but 3-dimensional is pretty similar. You just need to use trigonometry and math to solve it. So all right, so let's have a look of the first one. So now we have ball A and ball B. Okay, so momentum before equal to momentum after, straightforward. And then so let's look at the numbers. We put them together, so we get momentum before. So here we've assumed going to the right is positive, and that's very important because we're doing so much calculation. Sometimes questions can get very difficult, and we will forget to use some people use plus and minus. Like, we do it from the very beginning. From the very beginning, we're gonna say this is positive, and so the other direction is negative. And then at the end, I got a positive number 3.67, and that shows it's going to the right. Okay, so this question I don't want to talk too much about it because you've practiced it last year, and I got the answers here. You can have a look. So, and maybe if you're still confused with it, you can come and ask me or have a chat with other people, okay? And then the key thing is the 2-dimensional question, which is what you really need to practice this year. So you've already done a little bit of it last year as well. So I've given you 2 typical questions. So the first question is one ball coming hit this ball, and then they're going in 2 different directions. So these 2 add together will equal to the original momentum coming over here, okay? And the second question I've given you guys is a ball, and it breaking into 3 parts. So one going this way, one going this way, one going this way, okay? So 3 going this way. So as you can see, both of these 2 questions, I've given you a 90-degree. So why is that? It doesn't always go 90-degree, but for NCEA, they always give you a 90-degree because with 90-degree, then you can use Pythagoras, and also you could be using trigonometry to solve the question. If it's not a 90-degree, then you got to use sine rule and cosine rule, or you can decompose the components, which become a lot more difficult. So NCEA, they try to test you the physics ideas, so the math idea is not as important. So that's why they always give you a 90-degree. Okay, so you can be more confident that you all you need to do is Pythagoras and trigonometry. So if math is not if you're not very strong in math, yeah. Okay, sweet. So, and let's have a look. Again, P before equals to P after, and then I've just got to find out what is before, what is after. So I find out before, easy, because it's only the white ball. So that is going to the left. I've calculated, which is 73.5 to the left. So, and then P after equal P before, so I know P after is 73.5 to the left as well. So if you've done this, at least you would have get achieved, okay? So if a question is difficult, just give it a go, and so you can still get achieved. Okay, so after that, And then I know P after is the other two adding together. So once I know that, I can't use the numbers anymore. I have to draw a vector diagram, okay? Because 1 plus 1 is not equal to 2. So some students wrote that, and then they even draw the graph, and then sometimes they still go back and put the number in the equation. You can't put the number in the equation because we have arrows on the top. Oh, by the way, some of you guys might be from other teachers' classes. So when they use arrow, they might use arrow going this way, this way, this way, or this way. So when I do it, like I always just put an arrow to the right, because in math, when you put an arrow to the right, that actually means it's a vector. So it does not mean the direction is going to the right. It just means it's a vector. It has a direction. Okay, so that's why I'm going to continue this way. So I will always put arrow to the right to show there is a direction. So what is the direction? What direction it is actually in the question. So, but just scientifically and mathematically, like you should just put an arrow on the top. You don't actually give an arrow this way or that way, okay? But if you are used to that way and you find it easier for you to understand and solve problems, you can use that as well. So that's not a problem, okay? All right, so let's have a look, and then we're gonna draw the vector diagram. So vector diagram is very important. The rule we have is head follow tail. So that's the first rule. A lot of people would remember that rule. That's not a problem. But the second important thing is you have to look at the equation. And head follow tail, you have to follow the equation. You can't just add any head to any tail. So you look at the equation is P white after. So P white after is going down, and then add P back. So you're going to use the P white head, follow the tail of the P black, which is going upwards on the left. Right? And then that equal to the P after. The P after is from the tail to the head. Okay, so it's not head follow tail anymore. So now it's going from so you moved down and to here. So now what you have is from down here to here, this one and this one. So you've moved from here to here, right? So this is the arrow of the final product of these two add together, okay? So that's why, and then I do that, and then now I use trigonometry or Pythagoras to solve it. I got 95 kilometer per second, and still I need to calculate the velocity, so be careful. So I gotta divide the mass to give me the speed, and once I get the speed, because it is a vector and asking us about velocity, so I still have to calculate the direction. So I calculate that, I got 49 northwest. Okay, so we always go northwest or southwest or southeast, northeast. We don't go west, north. So that's why I've calculated that angle to state that it is north to west, okay? Some question could be asking you, so, oh yeah, what is the direction from the original direction? Then you gotta say, okay, the original direction is this way. So now my one is this way. So then you gotta say, oh yeah, it's 40 degree going this way, north compared to the original direction. So, or you just give it an angle, yeah. Okay, sweet. So have a look at the second example. The second example is one ball breaking into 3 parts. So the key is now still P before equal P after, but P before is 0. So now P after need to be 0 as well. So that's why we have this situation where PA at PB at PC is equal to 0. So I want you to think about, I think at year 11 we did this example, is like, you walk around, so you walk 10 meters this way, 10 meters this way, 10 meters this way, 10 meters this way, then your displacement is actually 0, even though your distance is 40 meters, right? So same thing over here. These 3 things need to add to become 0. How do they add to 0? So you have to go, okay, if I'm going this way, I'm going this way. I have to go back to the original position to make it become 0. So that's why you got this triangle where these 3 arrows all head following tail. So it doesn't matter you're adding A, B, C, or you go, okay, I'm doing C, A, B, or I'm doing B, C, A. At the end, you need to go back to that original position, which is 0. So once you got that graph, and then you calculate your data, you put your data in there, and then you will be able to solve the question, okay? And one key thing here, remember, is momentum stay conserved. So you can't just put velocity in there, say VA squared plus VB squared gonna equal VC squared. That does not work because these 3 objects have different mass. So that's why you have to be PA squared at PB squared equals to PC squared. Okay, so this is the question for conservation of momentum. So unfortunately, I don't have the booklet with me at the moment. So if you guys can have a look on the booklet, and just figure out like which part you should be working on. So based on what I taught you today. So today we're working on conservation of momentum, and we're looking at 1D situation and the 2D situation. So if you see the papers say, oh, this is a question, or if you see a question say, oh, this question I have no idea what it's talking about. If it's talking about like impulse or change of momentum or talking about force, then probably that we haven't taught that yet. So if we haven't taught that yet, don't worry about it, and then or just send me a message if you're not sure, and then see see if we've done it or not. So have a chat with your friends and see if they understand it. If they don't understand it, that probably means I haven't taught it yet. So so I'll be back in 2 weeks. So which is not next week, but the week after on Monday. So you will be missing. You're not missing any classes. I mean, I'm here. But I'll be with you guys in 5 lessons. So, and I'm going to keep teaching this way. This is how I normally teach it. I give the notes. I write down the notes on the board. I ask the student to copy it down and have a think about it, or I'll talk over it and then give students some examples. So here are 3 key examples, and it covers the majority of the questions, if not all of the questions in this topic over here. So, and then have a look of the question. So if you feel struggling, you cover the answer, you try to redo this question and see if you've got it, and then you try to apply it to other questions. Okay. All right. So so that's it for us today. So good luck, and send me an email and let me know how it goes, and I'll see you in the next video.